In this class, we will discuss a problem on minimum potential energy using the concept of minimum potential energy, which I had explained in the earlier video. We can find out the displacements at the required nodal points. I will explain that with the example of a spring system. So this is a spring system problem wherein we have three springs K1, K2, K3. They are the spring constants or the stiffness coefficients of the springs. Corresponding deflections or the displacements in those springs, I will take it as delta 1, delta 2 and delta 3. And there are two nodal points 1 and 2 here, which are where the external forces acting are F1 and F2, and the corresponding displacements at 1 and 2 we call them as U1 and U2. So let us assume that U1 and U2 they are in the direction of the applied force only. So if the values of U1 and U2 comes out to be positive after the analysis, the displacements are in that direction only. Otherwise, if you get negative value, then it is in the opposite direction. Now the constants are given like this. Stiffness coefficients of the three springs K1, K2, K3, they are expressed in Newton per mm. For the first one it is 40, second one is 60, third one is 80. So actually stiffness coefficient is a measure of the force that is required to cause unit displacement. And the external forces given are one is 60 Newton, F1 value, and F2 value is 80 Newton. Now this problem we can solve. So now we need to find the nodal displacements U1 and U2, which is subjected to the forces F1 and F2 with the spring systems K1, K2, K3. Now, for that we need to know the formula to find the strain energy for the spring element. Strain energy for the spring element is given by half into K into delta square, where K is the spring constant and delta is the deflection in that particular spring. And we know that as per the definition of total potential energy, it is nothing but the sum of work potential and the strain energy. So since they are of opposite nature, strain energy expression I will take it as positive and work potential expression I will take it as negative. This I have explained in the earlier lecture. Now let us write the strain energy expression as well as the work potential expression for the entire system. So since it consists of three springs here in series, so what you can write here is the total strain energy stored by all the springs is the sum of the strain energy stored by each spring. So that is half into K1 into delta 1 square plus half into K2 into delta 2 square plus half into K3 into delta 3 square. Coming to the work potential, since it is of opposite nature, it is negative. So force into displacement, that is the work done. So that is for at the node 1, U1 is the displacement due to force F1. At node 2, U2 is the displacement due to force F2. So since we have to take negative sign, minus F1 U1 minus F2 U2 becomes the work potential expression. Now the total potential energy pi is given by the sum of these two. So half into K1 delta 1 square plus K2 delta 2 square plus K3 delta 3 square minus F1 U1 minus F2 U2. So that is the sum. Now let us see what are the values of delta 1, delta 2, delta 3 for the given problem. So that value always depends on the position of the spring constant or position of the springs. Now if you take delta 1, so since this U1 is here, so delta 1 will be naturally equal to U1 because it is dispatched to the same displacement, and delta 2 also will be equal to U1, whereas delta 3, that is the displacement in the third spring, which has got stiffness coefficient K3, is the difference between these two, U2 minus U1, because it is attached at both the ends with these two nodes. So that is this you should be very careful. So delta 1 is also U1, delta 2 is also U1, but delta 3 is the difference between U1 and U2, U2 minus U1. Now from the principle of minimum potential energy, we know that the first derivative of the total potential energy with respect to the nodal displacement should be equal to 0. So that is the concept of minimum potential energy. So now there are two conditions here. Del pi by del u1 is equal to 0, del pi by del u2 is equal to 0. So using those two conditions, we can get two equations in terms of u1 and u2, and then we can solve them simultaneous equations to get the values of u1 and u2. Now let us use the first equation, del pi by del u1 is equal to 0. So here this is the expression pi. So this you have to differentiate with respect to u1 partially and equate it to 0. When you are differentiating the expression of pi with respect to u1 partially, u2 is taken as constant and the derivative of u2 terms becomes 0. So if you do that, you are going to get an equation in terms of u1 and u2 like this. This is simplified equation. You can see here when I have differentiated, I have taken u2 constant and only u1 derivative is written. And after substituting the values of k1, k2, k3 in the resulting equation and after simplifying, we get the first equation which is 9u1 minus 4u2 is equal to 3. Now the second equation is del pi by del u2 is equal to 0. So on similar lines, if you differentiate this pi, total potential expression, with respect to the second nodal displacement u2, treating u1 as constant and after substituting for k1, k2, k3 everything and simplifying, you are going to get the second equation minus u1 plus 4u2 is equal to 4. So now if you solve these two equations, third and fourth equations, you are going to get the displacements at the nodes u1 and u2. Since the displacements are positive, so whatever assumed direction of the displacements is correct. If any value becomes negative, you have to take the displacement in the other direction. So this is how we can find out the nodal displacements in a string system by applying the principle of minimum potential energy. The same problem can be continued for any number of strings. If there are three strings, then three equations you have to develop, and solving those three equations, maybe if you are asked to find at three nodes, you can always find out the displacement at three nodes. Similarly, it can be found out for at four nodes or for any number. Only thing is the number of unknowns, the number of nodal displacements, whatever unknown is there. If you want to get that, we need to develop so many number of equations. So number of equations should be equal to number of unknowns. Then only we can solve the equations and we can get the solution.